Hello. In this video we're going to look at some more quadratic functions. We're going to revise the features that we learned in the previous video, and then we're going to practice how to graph a quadratic function. On the screen you can see that we do have a quadratic function. We know it's quadratic for two reasons. First of all, if we look at the image, it is a parabola or a parabolic curve. And we know that that is the true representation of a quadratic function. And in this case, it is a positive quadratic because it's like a smile. It's nice and happy. Alternatively, we can look at the equation form where we see we have f of x on the left-hand side of our equals sign. And we know that that simply means that we have a function, its name is f, and that we're going to put inputs into it, and then to get the outputs we're going to perform this rule, so these calculations, the right hand side of this equation. Each time we see the x, we know that that is the inputs that we're going to put into the machine. So for this function, to find each input's output, we must square the input, because this is x squared and x is the input. The input squared, then we must add 3 lots of the input. We know that 3x means 3 times x, so 3 times the input, and then we must take 5. Now, as we learned in the previous video, that the coefficient of the x squared term, so remember that the terms in algebra all start when there is a sign. So here's our first term. It's like the parts of our equation. Here's the second term, and here's the third term of this right-hand side. Now, this x squared term then has a coefficient, a number in front of it that's attached to it. And that number is positive 1. If you can't see a number there, but you can see the letter, that means there's one lot of it. This is one lot of x squared. So it's a positive 1. We've just made it kind of invisible. We don't like to write the number 1 when we have one lot of it. But it's positive, it's not negative, it's not minus x squared. So because this number is positive, then that makes the entire quadratic function, the parabolic curve, positive, the smile. If it was negative, then it would be the frown, it would be upside down. Now, if you were to just temporarily ignore this first term and we were to just look at these last two, then they should actually look quite familiar from when we did linear equations. If you recall, a linear equation had just an x term. It didn't have x squared. And it also had a constant, so a number on its own, not attached to a letter at the end. And we learnt that with a linear function, so when it's plotted it was a straight line, that these two numbers are quite special, they're important, and they help us to know a little bit about what the line will look like. For example, the number in front of the x refers to its steepness, its slope, or its gradient. And the constant is the y-intercept, so the number on the y-axis where the line crosses. Well, there are some similar properties with the quadratic function. We'll start by looking at the constant, the number that's not attached to a letter, the -5 in this case. Well, just like with a linear function, this refers to where this function, and we know it's a parabola, a quadratic function, crosses the y-axis. So the y-axis is the vertical axis, this one here that goes up and down. And as you can see, this is this function. And look, there's -5 on the y-axis. It does indeed cross the y-axis at -5. So -5 is the y-intercept. If you intercept something, that's when you cross it, you cross paths with it. You might hear in a movie about the cop intercepting the criminal. So they've caught hold of him, they've crossed paths here. So that's the similarity with the linear function and the quadratic function. So that's quite helpful when checking your graphs after you have plotted them. So we should expect to know where it crosses the y-axis. Now, with quadratics, this middle term coefficient, so the number attached to just the letter on its own, it actually doesn't refer to the steepness. And in fact, if I change this, at the moment this is +3, a +3. Watch what happens if we look at other values. There's 2x, it moved to the right, 1x, it's moved to the right again. So it's actually helping us with the location along the x-axis for a quadratic, but we'll be looking at that in more detail later on in the course. So for now, we really want to make sure that we know when a function is positive or negative and why, so looking at the coefficient in front of the x squared, and also that the y-intercept is the constant, the number that's not attached to a variable, a letter. So to help us, I have done an example question like you might find in an exam. In fact, this is a question that's taken from the exercise that I've asked you to do 2 similar questions from this same exercise. So this is question 9 from exercise 31.5. Now, I would like you please to copy this example into your notes copy. So you may prefer to do it step by step as the video is playing and to pause and add to it so that by the time the video is finished, your example is also finished too. So the question states to draw the graph of the function. It doesn't tell us what type of function it is. We have to figure that out from looking at its equation, looking at its notation. Now we see that we don't have f of x, g of x or h of x, we simply have y. Remember that f of x, the f with the bracket and x inside of it, is exactly the same as the y. It both means the output. So the outputs of this function are as a result of the rule, which is the right hand side of this equation. And we've got minus 2 lots of x squared plus 5 lots of x minus 1. So straight away, I know that this is actually a quadratic function because there's an x squared. If there was just an x with no square, then it would be linear. And also, we're not studying these at the moment, but if it was x cubed, then that would be a cubic function. So because there is an x squared, we know that it's going to be a parabola, it's going to be a curve. And next I can look at the number that's attached to the x squared, and it's negative, it's minus 2. So that helps us know that this is not only a quadratic function, but it's a negative quadratic function, and that when it's graphed, it will look like a frown, an upside down smile, or an N-like shape. And we also see that the constant on the end is minus 1, which means that it's going to cross the y-axis at minus 1. So this is a description of the function, and we're told a little bit of information about what inputs are going to go into this function, and that's the domain. So the official definition for the domain, if you can recall, is the complete set of inputs. So what we start off with before we perform this calculation. And you'll see that we have minus 1 is less than or equal to x, which is less than or equal to 4. Sounds confusing, but it simply means that x, our inputs, range from the number to the left, minus 1, all the way up to and including the number on the right to 4. So the numbers minus 1, 0, 1, 2, 3, and 4 are our inputs to go into our quadratic function. And this here means that the inputs, x, belongs to the set R, which is the real numbers. And they're all the numbers that we have studied so far on your junior cycle course. So we don't need to worry about that too much. Okay, so as before with the linear function, we start off step 1 by drawing an input-output table. So there are 3 columns. Now, a quadratic function has a number of calculations to do, so it does require a little bit of workings. So you'll want to leave a few lines for each input to calculate the output. So you've got your inputs, which we know are x, and they will become your x coordinates for our points later on. Then you have the middle column, which is the rules. So at the top in the headings, you just write out the right-hand side of the equation. And then for your workings for each input, you'll simply be swapping the x for that input. So when it's -1, so beside -1, instead of -2x squared, it's -2 lots of -1 squared. And then we have the third column, which is your outputs, your answers. After we've changed the x to this input, what do we get when we work out this equation? When we finish doing the BIMDAS or the POMDAS or BEMDAS, whichever it is that you've learnt, so making sure that you do these operations in the right order, you will get an answer, and that becomes your y value to plot for your outputs. Remember, each input and output will be a point that we'll end up drawing then to represent our parabola. Okay, so as you can see, I have got 3 lines of workings for each input. It's really important that we do show as many workings as possible. In case we get our answers incorrect, we're still going to pick up attempt marks. So as we said, we're swapping the x each time for the input to the left. So you'll notice that my first line here is just repeating the rule again, which is our function, the right-hand side of the equation. And then, as always, when you substitute a value in place where there once was a variable, so when we swap a letter for the number that we now know it represents, we must put a bracket around it. And that's to help us to remember that -2x squared means -2 lots of x squared, -2 times x squared. So that's helping us to remember that this -2 and the result of this squaring will be multiplied together. So we've got -2 times -1 squared plus 5 times -1 minus 1. So we'll follow our BIMDAS, as we said, and we know that the indices, the powers, must be done first. So in my second line of workings, all I've done here is I have performed this power. So -1 squared, well, to square something, it means to times by itself. So -1 times -1, and 2 minuses make a plus. So we end up with +1. So it's now -2 lots of +1. And then I've also done this multiplication here, which was +5 times -1, a plus times a minus. Well, they're not the same sign as each other, so they're not going to get on well. There's going to be a negative outcome. So it ends up with a minus, and 5 ones are 5. And then we still need to take 1 and just bring that down. So next I can now multiply these two together. -2 times 1 is -2. And I'm still going to take away 5 and take away another 1. So -2 take away 5 makes -7. And take another 1 makes -8. So there's my answer. So when the input is -1, the output is -8. And we will do the same procedure then for each of the inputs in our domain. So remember, the domain was -1 all the way up to 4. So we have each of the whole numbers then from the smallest, the number to the left, right the way up to the number to the right, which was the largest. And we've done exactly the same thing for our rule, our calculations, but each time the number in the brackets is the input to the left. So it's 1 here for the input 1. 2 here for the input 2, 3 for 3, and 4 for 4. Let's just check another one of these calculations so you can see where the BIMDAS is playing out. So with BIMDAS, you first of all do a bracket with a sum in it. Well, we don't have a bracket with a sum in it. we only have brackets that represent multiplication, so that doesn't apply here. Next, the I stands for indices, our powers, and we do have a power. We have 4 squared. This power is attached to the bracket, so it's a square of what's inside the bracket. Now 4 times itself is 16. Now after I in BIMDAS, we have multiplication and division. We don't have any divisions here, so we don't have to worry about that, but we do have some multiplications. We now can do minus 2 times 16. A minus and a plus makes a minus, and 2 16s are 32, so minus 32. And we also have positive 5 times positive 4. 2 positives make a positive, and 5 fours are 20. So it's adding 20 and minus 1. So we've got minus 32 plus 20. That makes minus 12, but then we need to take another one away. So our answer, our output, is minus 13 when the input is 4. So after you've finished drawing your input-output table, you now have your inputs and all the outputs for those inputs. You're then going to go to step 2, where we write out the couples or the ordered pairs. And we know that that's a complete set, so we have curly brackets, and then inside the curly brackets we have a small ordinary set pair of brackets where we write every input followed by its output. So if you look, minus 1 and minus 8, and there's our first couple. Each of these couples then are separated themselves by commas. So this one here is the third input and output. So look, third one down, 1 and 2. 2 and 1. 3 and minus 4. And 4 and minus 13. Now those couples are now the points that we are going to plot on our Cartesian plane, our XY axes, so that we can draw our quadratic graph. So that's the next step. Step 3 is to draw the couples as points onto your XY axes. Now notice how I have really made use of all the space that I have got left. And this is really important that you do the same in an exam as well, so that you can be as accurate as possible. If you just automatically draw your X in the middle of the page, like with this one, you'll see that there's a lot of low, a lot of the graph is underneath the X-axis. It would end up being very small and only kind of this big. So it would be a bit too cramped. So before you start drawing, you need to carefully look at your couples and your numbers in particular for the X's. So the first numbers we know range from minus 1. It's sometimes easier to look down here. Minus 1 is the smallest, going up to 4. So I knew that I had to draw on the X-axis from minus 1 to 4. I like to go a little bit extra in both directions as well, so that it's not completely, our graph isn't finishing right at the edge of the page. Now, because that the distance between minus 1 and 4, there's only 5 numbers there. So I knew that I could make a good, decent amount of space in between each number, each value. So I decided to pick 3 boxes in between, because when I counted my boxes across the page, I could fit 3 in between and it would still have space either side. So you'll see I've gone to minus 2 and there's 4 and there's a little bit extra as well. So it's really made my graph cover this, that sort of almost the whole of the page. Now what's really important is if I've picked 3 boxes between minus 2 and minus 1, then I've got to have 3 boxes between minus 1 and 0, 3 boxes, 3 boxes, 3 boxes. Make sure that you have the same amount of space in between values on the same one axis. So all of these numbers on X have 3 boxes between. Now you'll notice a very different scale for the Y axis, because I had a lot bigger range of numbers. We had a number minus 13 and we had a positive 2. That was the largest number. And this is the smallest number, but that means it was quite big. And it meant that I didn't have enough boxes when I counted my squares in my book just like you will count your squares in your exam paper. I didn't have enough of them to have even 2 boxes in between each number, because to get from -13 to 2, that's 15 spaces. So if I wanted 2 boxes between them, that would be 30 boxes, and I didn't have 30 squares in my book going down here, which told me that as I did have 15, I'm going to have just 1 box for every new value. So you'll see that from 0 to 1, there's 1 box. From 1 to 2, 1 box. So every single number on my y-axis is separated just by 1 box. So it's all consistent. And remember that you must have 0 at the intersection where the 2 axes cross. And then you must go from 0 out to 1. It's one of the mistakes that people make, is they can't think of 1 here as the starting point, but it's always 0. And then you move to -1, +1, +1, -1. Okay. So remember that you draw with your pencil, make it nice and sharp using your straight edge like a ruler, and you label your axes, X and Y, and then your numbers, your scale can be drawn in pen, and that you put these little dashes, the markers, to show exactly where those numbers are. Okay, once you have your scale, then it's time to start plotting your points. So let's take this first one. It's -1, -8. So that means its closest number on the x-axis is -1, and the closest number on the y-axis is -8. So here's the x-axis, -1, and the y-axis has -8 here. So if we were to go vertically below -1 and horizontally across -8, there's the point there. And then the same for 0, -1, 0 on the x, and -1. Now notice that this is a special point because this is the y-intercept. It's where our curve crosses the y-axis, and that's exactly what we were expecting from the function itself, this constant -1. And you can see that we were correct here. Now we've got 1, 2, so 1 on the x, +2 on the y, that's this point here. 2, 1, 3, -4, and then lastly 4, -13. So I have all my points now on my diagram. Now the next part then is the tricky part. It's drawing this smooth curve. Notice that there are no jagged edges. I haven't got any excess pencil either. So whilst I did actually do a technique of very, very light pencil movements like this, but then I've barely touched the page, so that if I decide, no, I'm not on track, my pointer's up here, for example, I'm going to the left, then I could very easily rub that out without making any mess on my page. You can see it's completely gone. So really, really light movements. And what's happening is with this feathering, it's called feathering, it's like small movements, and the palm of my hand is firm on the page to give me extra support, is that your pencil width is actually still quite too thick. But the idea is that this just becomes a guide, and then when you find your correct line, the one that you're happy with, you can then very carefully go over that again then a little bit firmer, and then you'll be able to rub out the feathering parts that were there before. Oh, I've just managed to use a rubber that was dirty, so there we go, apologies. Okay, so that's also another handy tip. Make sure that when you're using your rubber that it's nice and clean, so that when you rub out the feathering, it's nice and neat. So I actually just did this parabola about 5 minutes ago, so you can see that you can maybe when you look very close, you can see there were parts where I had pencil lines, but I've really been very careful to remove any of the extra lines that I didn't want. Now, what the examiner does is the examiner looks carefully at each of the points to check that your parabola does go exactly through them and that it's not a jagged edge and then changes direction. So the idea is that you shouldn't really be going from one point to another, but you're traveling through that point to get to the next one. You're always looking at another point ahead. Now, the reason I chose this question to do with you was on purpose. I chose this question because this is a harder question than one that I looked at with you yesterday or in the previous video, was because each of our points were not symmetrical opposite each other. So when the points were there without the curve, first of all, it actually wasn't that easy to spot where this maximum point, the highest part of this curve, should be. And it wasn't until I started from the left-hand side, moving towards the next point and then the next one, that I realized that if I had it, the peak of my parabola here, that it would be too sharp a point to make it to my next one. It would end up being a little bit jagged like this kind of thing. And that even if I tried to smooth it, it just wasn't going to work. So that helped me realize that this point wasn't the peak, that I was going to have to continue a little bit further on. So what I did then was I went and started from the other side, and this was the hardest section here because it was a long distance from one point to another. Again, of course, it's always freehand, no straight edges ever to be used when drawing a quadratic function. But then when I started to get this smooth curve, it became quite apparent that if we had the maximum point here, that it would be nice and smooth. So it really is a type of question that you would need to practice several times. It does require a lot of patience, and for this reason, it's why you have a double class today, and yet I've only given you 3 questions to do because I want you to spend time on them. So we almost have finished, but not quite. So step 4, we've connected the points, ensuring that our curve is smooth. So as I said, the examiner will literally tick off these points to check that your curve goes through them and that it is nice and neat. And please, nobody use a pen to draw a function. Okay, you can use that to label your axes, and then we label our function like we did the linear one by simply writing the name just like it was given in the question anywhere beside the curve that we've just drawn. And then the last thing I'm going to do now that I've finished drawing my line is I'm now going to label my points, which I couldn't do before because I didn't want to block the view of my curve. I was worried if I'd have written my point here, then I wouldn't have been able to have seen where to put my pencil. So I've left writing the points out till the very end, and that's absolutely fine. So there we have it. There's our quadratic function, and as expected, the y-intercept is at -1, and it is indeed a negative parabolic curve, just like we predicted from the negative coefficient of the x² term. One last thing then, just for fun. Why did the student get cross with the teacher for calling her average? Why? Because it's a little bit mean. Thanks for listening, and I will see you in the next video.